Hello everyone. So today we will talk about strain transformation. In previous two chapters, we have introduced the methods, equations to do stress transformation. And we introduced how to draw Mohr circle and use the Mohr circle to find out the principal stresses and the maximum shear stress, including the in-plane maximum stress, maximum shear stress, and the maximum absolute shear stress. Okay, so I believe you have all understood why we need to do stress transformation and why we need to find out the principal stresses and the maximum shear stresses. Okay, so now why do we need to do strain transformation? Actually, similar to that, why we need to transform stress. Okay, assume that you have a simply supported beam subjected to loading. Then you can separate out a arbitrary element. I believe now if you know the magnitude of the load and the dimensions of the beam and the position, so you can analyze the normal stress, shear stress at this point. You can analyze the strains. But how about along other directions? If we know this element, you can do the stress strain analysis. But how about the strains along other directions? I can not along these directions, but along other directions. Okay, if you have a different inclined coordinate system, so what are the strain values along those directions? Okay, so in this way, we need to use the strain transformation equations or strain Mohr circles, okay, to find out these problems. So today our objectives include strain transformation, and then we will talk about how to measure strains in the real-world structure. Okay, we will use the strain gauges. Then it's other equipments, devices. You can measure the strain values in different directions, and then we can do strain analysis based on our theories and to solve the strain rho sets. Okay. Then before the theory part, let's review the stress transformation equations. Okay, here I just listed the equations we derived in previous two chapters that we can use to do stress transformation and finding out the principal stresses and the tau max. Okay, so just assume that in the beginning we have a stress element. Assume that we had this stress element. You have sigma x, sigma y, tau xy. And then after rotation, you get another stress element shown here. Okay, here is a sigma n, sigma t, and tau nt. Okay, and here you get an angle that is theta. Okay. So this is the stress transformation, okay, from sigma x, sigma y, tau xy to sigma n, sigma t, tau nt. Okay, those are the equations where you can calculate the value of tau sigma n from sigma x, sigma y, and tau xy, and calculate the tau nt from sigma x, sigma y, and tau xy. Okay, of course we have the third equation. That is the sigma t, right? So you can just use a similar equation to the first one, right? It's just sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta and minus tau xy sine 2 theta. Right, you get the third equation. Those are the three equations you can finish your stress transformation. Right. And then to find out the maximum normal stresses or the principal stresses, you need to do a rotation of theta p. Right, this theta p can be determined from this equation. It's just a tau 2 times theta p equals a tangent 2 times theta p equals tau xy over sigma x minus sigma y over 2. Okay, you can also have the equation here to calculate the values of the two principal stresses, and this is the equation to calculate the tau max. Okay, we can also find out these values through a Mohr circle, or you can also do stress transformation in a Mohr circle. Okay, just let's review the whole process, since later you will use this process to draw the strain Mohr circle. Okay. So first of all, we need to determine a coordinate system. This is the x-axis, and we denote it as sigma axis. Okay, this normal stress axis, and then we'll find a tau axis. Right, the y-axis is the tau axis, but sometimes you can see that people like to draw the tau axis downward, so the positive direction downward. Okay, so in this way, you can keep the rotation, the direction of rotation consistent with the stress element. So it has its advantage, but you can do it either way, just depending on your understanding. Okay, so in this coordinate system, to draw a Mohr circle, the first step, we will just find the first point. That is sigma x, and we find the first point sigma x tau xy. Then the second point sigma y. And here is sigma y negative tau xy. Okay, then you connect these 2 points. Then use it as a diameter to draw the circle. Yes, I got a good circle. Okay, then based on this circle, you can do some analysis, and the first step, we will find out the center, right, the C. So what is the coordinates of the C? Its x coordinates will be, obviously, it will be sigma x plus sigma y over 2, 0. Okay, then how about the R? How about the radius? Here is the radius of the circle R. Right, to find it, we just need to use this triangle. Right, so in this triangle here, this length will be sigma x minus sigma y over 2. Right, and here will be tau xy. So obviously the R will be sigma x minus sigma y over 2 square plus tau xy square root. Okay, so in this way, using the C and R, so we can find here is the maximum normal stress. Okay, let's denote it as the sigma P1. And here you get the sigma P2. Okay, so using the C and R, the sigma P1 would be C plus R, and sigma P2 would be C minus R. Okay, since the C is sigma x plus sigma y over 2 here, okay, plus or minus the R is here, okay, so the C plus or minus R, you derived this equation. Okay, then what is the maximum tau? The maximum shear stress. Since here is your tau axis, so the maximum values of tau is here, all here, right? This is the negative, positive. So you get positive or negative R, right? So this is positive or negative R. So you get this equation. Apart from these things, you can also do analysis and to find out the features of them, right? So for example, at the position where you have the principal stresses, you have the maximum normal stresses, what is the tau value? Right, so when you have the principal stresses, tau should equal 0, right? Since those 2 points are just on this on the sigma axis. Then how about the normal stress values when you have the maximum shear stress? Just right on these positions, on these 2 points, you have the maximum shear stress. So the normal stress will be normal stress along these 2 directions will be the same, right? Those are sigma average equals sigma x plus sigma y over 2. Right? And you can have other methods based on the Mohr circle. You can have other methods to find out the tau max. Right? So the tau max is just equals R, right? Or the diameter over 2, right? So what is the diameter? Diameter here equals just the sigma P1 minus sigma P2, right? Over 2. Okay? So this is the other method, the other equation that you can use to find out the tau max if you know the principal stresses. Okay, so those are the equations and the Mohr circle that we can use to do stress transformation or finding out the maximum values of normal and shear stresses. So in this section 8.3, we will do strain transformation and measurement. Okay, we will solve the strain rosette to find out the strains in real-world structures. Okay, before everything, let's review the concepts of strains. Okay, what is shown here is a 3-dimensional element where you can see 6 faces, right, on which you can find different stress values, stresses. Then here in this coordinate system, you have sigma x, you have sigma y, you have sigma z, right? Then you can also have the tau xy here, right? Or this is tau yz here. And your tau xz here. Okay, you have these stress components. So when this element is subjected to stress components, it will have strains. Okay, the strains have so many components as noted here. You have sigma, you have epsilon x, epsilon y, epsilon z, and the shear strains gamma xy, gamma yz, gamma xz. Okay, so the normal strains are easy to understand. I just find out the elongations along different directions and over the original length. Right? So the epsilon x equals dx prime minus dx over dx. Right? So in the same ways, you can find the epsilon y and epsilon z. Then how about the shear strains? You can see here this angle between x and y direction is sigma xy. So after deformation, you get a theta xy prime. So its original value is pi over 2. Okay. So the strain gamma xy is calculated by pi over 2 minus gamma xy prime. It's the angle before deformation minus the angle after deformation. This is a little different from the definition the definition of the normal strain. This is a normal strain. You use the length after deformation minus the length before deformation over the original length. Right. So let me ask you this question. If this theta xy prime is smaller than 90 degree, it becomes smaller. Is that a positive or negative shear strain? If you recall earlier chapters, you should still remember that this is a positive shear strain. Okay, when this angle between x and y axis becomes smaller, we say its a shear strain is positive. Okay, so when this theta xy prime is smaller than 90 degree, the gamma xy is positive. When it's larger than 90 degree, well, this gamma xy is negative. Okay, so in the same ways, you can also define the gamma yz, gamma xz. Okay, so these are the definitions of strains of the 6 strain components. Now, how about strain values along arbitrary direction, n, t, which are perpendicular to each other, and the gamma nt? Okay, the epsilon n, epsilon t, and gamma nt. We can, of course, we can define them in similar ways, but how can we find them out? Well, if we know this sigma x, sigma y, and gamma xy, and we know angle of rotation, so can we find out the epsilon n, epsilon t, and gamma nt in similar ways to the stress transformation? Well, those are the questions we will answer in the next several slides. Okay, in 3-dimensional cases, these transformations will be complicated. So again, we just simplify it into a 2-dimensional case. We just focus on the xy plane. Okay, the xy plane, and we will show you the general equations for plane strain transformation. In previous sections, we dealt with the plane stress transformation in xy planes. Okay, so here we again focus on xy planes, and we do plane strain transformation. Okay, first of all, in these slides, I listed here those equations we use for stress transformation. Then on the left-hand side, I listed the equations for plane strain transformation. You can compare them one by one, so you can see that they are very similar, apart from some small differences. We can actually do analogy between them. Okay, you can see that if you can find a sigma x here, in the stress equations, you will be able to find a epsilon x in the strain equations. If you can find a sigma y in the stress equations, you'll be able to find a epsilon y in the strain equations. Okay. If you can find a tau xy here, do you think you will be able to find a gamma xy in the strain equation? Yes, you can, but it's not directly gamma xy. It's gamma xy over 2. Okay. This is the only difference between these equations. Okay, let's summarize them here. If you have a theta x in the strain equation, it will correspond to a epsilon x. Theta y will become epsilon y. Of course, you have other things like sigma n. It will become epsilon n. Right? Sigma t will become epsilon t. Okay. Then the tau xy will become gamma xy over 2. Right, not gamma xy. In the same way, if you have tau nt, it will become gamma nt over 2. Okay. Just everything about shear will become shear over 2. Okay. So that is the difference. Then let's highlight the differences in these two equations. So first of all, you can see here in the first two equations, you have a tau xy on the stress equation, and you will be able to find a gamma xy over 2 in the strain equation. The second one, the same way, tau xy here, gamma xy over 2 here, and tau nt here, gamma nt over 2. Okay. Then in the third equation couples, you will see here on the in the stress side, you have over 2 here, but you don't have over 2 here. On the fourth equation, you have a tau xy square, and here gamma xy over 2 square. And the last one, tau xy square, gamma xy over 2 square, and tau max, gamma x over 2. Okay. In the similar ways, since we derived in the previous slide, so we have other equations that you can use to determine the tau max. This is based on the Mohr circle. You have a tau max equals the theta p1 minus theta p2. That is the diameter of the Mohr circle, right? So it's over 2. Now how about on the strain parts? On the strain part, okay, what does that mean if you write the principal strain P1 minus principal strain P2 over 2? What does it equal? Would that be gamma max? Or gamma max 2? Gamma max over 2? Okay. According to this analogy, we should have gamma max over 2 equals epsilon p1 minus epsilon p2 over 2. Right? So in that sense, the gamma max maximum shear strain will be sigma p1 minus epsilon p1 minus epsilon p2. Okay, those are the equations. Well, you can use these equations to do transformation, or you can see what we can do later. Okay, we can also draw more circles. Okay, we can also draw a string Mohr circle. Okay, here this to draw a Mohr circle, we just start from what is known. We know the string elements, string components of an element. You have epsilon x, epsilon y, and gamma xy. Right. But to draw the Mohr circle, we will not use these three. We will use epsilon x, epsilon y, gamma xy over 2. Okay, those are the three things we will use to draw the string Mohr circle. Okay, so first of all, you need to define the coordinate system. Right, so the coordinate system, you have the x-axis, that is epsilon. Right, and the y-axis, again, you can draw the y-axis downward, so that you have a consistent direction of rotation in the Mohr circle and in the string elements. Okay, so here is the axis of gamma xy over 2. Okay, so after you determine this coordinate system, you will find the 2 points to draw the circle. Okay, the first point will be epsilon x gamma xy over 2. Okay, this is the first point. And the second point will be here. That will be epsilon y negative gamma xy over 2. Then you connect them using this blue line. Then use it as a diameter to draw the Mohr circle. Right. So here you can see what is the center. What is the center? The center would be epsilon x plus epsilon y over 2. Right. So here is your epsilon x, epsilon y. This is the center, C. Then how about the radius? In the same ways, we can use this triangle to find out the radius. Well, if you know here, this length would be sigma x minus sigma y over 2. And here, this length will be gamma xy over 2. Right? So the r will be epsilon x minus epsilon y over 2 square plus gamma xy over 2 square root. Okay. So then, what is the principal strings? Okay, the epsilon p1 will be just c plus r, and epsilon p2 will be c minus r. Okay, you know the c, you know the r, so you can see if you are able to find these equations. Okay, this equation here. This is the c coordinates, so plus minus the r. Okay, this is how we can derive these equations from the Mohr circle, from the string Mohr circle. Okay, you can also examine what are the maximum values of gamma of the shear string. Okay, the maximum values are denoted here and here. Okay, and this is 2 points. You will have the the maximum shear strain over 2 equals R. Okay, equals R. It can be a positive or negative value. So you get this equation. Okay, then that means if you want to answer the question, what is the maximum shear strain? That should be 2 times R. Okay, so on the Mohr circle, you can also do the transformation, right? If you want to know the strain components and the position after rotation by angle theta, right? Just you can transform it from the blue colored line to the green colored line. After that, what these points, use these 2 points, you can denote the strain status at that position. Okay, if you want to find out the plane strain position, you just rotate it by 2 times theta p. Okay, you will get this diameter, and this is 2 points to denote the strain status. Okay, I also provided a web page and a video here, so you can click them to find out more details about the strain Mohr circles.